So let's go back to the original calculation that we started off with. For the specific heat, Cv over nkb is going to be 3 by 2 F plus 5 by 2 of Z divided by F plus 3 by 2 of Z plus 3 by 2 T F plus 3 by 2 of Z whole square F plus 3 by 2 Z dF plus 5 by 2 dt minus F plus 5 by 2 of Z d of F plus 3 by 2 dt. This expression now, what we will do here is we will use this over here and this over here, which means this gives us 3 by 2 t F plus 3 by 2 of Z F plus 3 by 2 of Z times 1 over Z dz dt minus F plus 5 by 2 over Z times F plus half over Z times 1 over Z dz dt divided by F plus 3 over 2 of Z whole square. And therefore this becomes 3 by 2 F plus 3 by 2 over Z whole square minus F plus 5 over 2Z times F plus half of Z divided by F plus of 3 by 2 Z whole square 1 over Z dz dt. So we can simplify this further and we will have 3 by 2 t times, this gives you 1. If you take this divided by this gives you 1, and you have 1 minus F plus 5 by 2Z F plus half of Z divided by F plus 3 by 2 of Z whole square. The whole thing in a bracket, and I have 1 by Z dz dt. So that the specific heat over nkb, do not forget the first term, I have 3 half F plus 5 by 2 of Z F plus 3 by 2 of Z plus 3 by 2 t 1 minus F plus 5 by 2 of Z F plus half of Z F plus 3 by 2 Z whole square 1 over Z dz dt. Now it remains for us to determine this derivative dz of dt, and I note that this is not very simple task. Why is that? Because it's not that z is equal to e to the power beta mu, but one can be tempted to just take the derivative of beta with respect to t and be done away with, but one has to also note that the chemical potential needs to be determined as a function of t. So this is a very complicated, non-trivial task, but you can simplify this. For that, we start off with the expression for the particle number, which was n was gv over lambda t F plus 3 half Z. And if you do not recall how we got this here, we wrote down the total particle number as the sum over the average occupation number in the energy levels in the k energy levels, and this we knew that has the expression Z inverse e to the power beta epsilon k minus 1, and this sum into an integral in terms of the density of states G epsilon D epsilon, where epsilon goes as epsilon to the power half, G epsilon goes as epsilon to the power half, and then we got this result like this. So this means that n lambda t over GV is going to be f plus 3 by 2 of Z. Good. Now I want to take a derivative with respect to temperature in the left hand side as well as in the right hand side. ddt of f plus 3 by 2 of Z. The right hand side is very easy to evaluate. We will do that in a straightforward way by writing ddz. So the derivative with respect to temperature, I'll convert it into a derivative with respect to z, and then I will have dz of dt. But this one I know, because f plus m d of m, I derived this as minus 1 over z f plus m minus 1 of z. So it follows that this derivative is minus 1 over z f plus half, 3 half minus 1 is half, z dz dt, so that I have minus f plus half of z 1 over z dz dt. You see, in the right hand side I precisely have the term which I am looking for, which is already there in the specific heat. I now have to evaluate the left hand side. The left hand side is ngv dt of lambda t. Lambda t, I know I will write down as alpha t to the power minus 3 half. Alpha is a constant which I am not very interested in right now in my expression, so that ln lambda t is ln alpha minus 3 half ln t, and therefore 1 over lambda t d lambda t dt is going to be minus 3 by 2 t, which means d lambda t dt is going to be minus 3 by 2t times lambda t. And if I replace this expression over here, I come up with n lambda t over gv minus 3 by 2t. But surprisingly, this quantity I have already started off with, so which is f plus 3 by 2 of z. So if I use all this information now, this part, and then this going in the left hand side, I have my mistake. There cannot be a minus here. It's just going to be plus. So this is plus. The equation we derived was plus here. I have f plus half of z times 1 over z dz dt is going to be minus 3 by 2t f plus 3 by 2 of z, so that 1 over z dz dt is going to be minus 3 over 2t f plus 3 by 2 of z divided by f plus half of z. And this result now I take from here and substitute it over here in the expression for my specific heat, so that I come up with Cv over nkb was 3 by 2 f plus 5 by 2z f plus 3 by 2z plus 3 by 2t 1 by z dz dt 1 minus f plus 5 by 2z f plus half z f plus 3 by 2 of z whole square and this is going to be plus 3 by 2t. So this over here, I have minus 3 by 2 and 1 by times 1 by t, and I have f plus I have f plus 3 by 2z divided by f plus half of z 1 minus f plus 5 by 2 of z f plus half of z divided by f plus 3 by 2 of z whole square. Complete the bracket. Take this inside. If you take this inside, then you see, first of all, this t and this t gets cancelled out, and you have the product of the minus gives you this, so product of minus and plus gives you a minus, so that you have minus 9 by 4, and then the first term is f plus 3 by 2 of z divided by f plus half of z. Now you notice that one factor of f plus 3 by 2 of z cancels with one factor here, and the f plus half in the numerator is completely cancelled by the f plus half in the denominator, so that you will have f plus 5 by 2 of z divided by f plus 3 by 2 of z, and then you have a minus of 9 by 4 and a minus over here, that gives you 9 by 4. If you follow this carefully, you see that this term has the same form as this term. The prefactors are different. We simply add up, which is 3 by 2 plus 9 by 4, which gives you 3 by 2, 1 plus 3 by 2. That is 5 by, so 3 by 2 into 5 by 2, which is 15 over 4, and you have CV over NKB is equal to 15 over 4 f plus 5 by 2 of z divided by f plus 3 by 2 of z minus 9 by 4 f plus 3 by 2 of z and divided by f plus half of z. And this is the expression that we were originally after. But we have to run checks. And the first check that we have to run is, does it match at Tc with the expression we had earlier when we derived the specific heat for temperatures less than Tc. Now you see the expression, and if you look at focus on the second term in the expression, you see that in the denominator I have f plus half of z. And here for this function m is less than 1, so that as z tends to 1, this f plus half tends to of z tends to infinity. So as you keep on decreasing the temperature, the denominator blows up, so that the second term starts contributing less and less and less until at Tc this vanishes completely. So at T is equal to Tc, you simply have Cv over Nkb is equal to 15 over 4 f5 by 2 plus 1 divided by f plus 3 by 2 of 1, which is 15 by 4 zeta 5 by 2 and zeta 3 half. Exactly matches the specific heat that we did when we looked at the case T less than Tc. For specific heat T less than Tc, I know that Cv over Nkb goes as T to the power 3 half. Right? Interestingly enough, if you put in these numbers for the Riemann zeta function, you will see at Tc this number is approximately 1.92. It is more than what Dulong-Petit's law tells you. That is essentially 3 by 2 kb. right, nkb. So well, in this case it's going to be 3 by 2. If you now just go back for a second, go back to the specific heat, this expression, and look at very high temperatures, do I get back my classical result? That is my second check. So I know that for high temperatures, if I plot z as a function of x, where x was n lambda t over gv, this is the behavior, and this is 1 beyond zeta 3 half, and for small enough values this is going to be z is equal to x, and we are interested in this region for small enough values of x, so that I have z is approximately equal to x equal to n lambda t over gv. If that is the case, then f plus 5 by 2 is approximately equal to z, f plus 3 by 2 is approximately equal to z, and f plus half is also approximately equal to z. That's a leading order correction. That's a leading order term. So that I have Cv over nkb for temperatures much larger than the critical temperature. I have 15 by 4 minus 3 by 2. Then this answer is going to be, if I take 3 by 2 common, I have 5 by 2 minus 1, which is going to be 3 by 2 into 3 by 2, that is 9 by 4. And there is something wrong here. Yeah, so I know where the mistake is. For very high temperatures, for T much larger than Tc, therefore Cv over nkb becomes 15 by 4 times z divided by z minus 9 by 4 times z divided by z, which is 15 by 4 minus 9 by 4, which is equal to 6 by 4, and that is exactly equal to 3 by 2. So far away from the critical temperature, you get back the classical result of Dulong-Petit law. So if I now want to plot the specific heat, for T less than Tc, Cv over nkb goes as T to the power 3 half. So this is Cv over nkb, right? If you have forgotten how we got this result, then I know that beta p was g over lambda t f plus 5 by 2 times z, and from this we calculated u was 3 by 2 kbt gv over lambda t f plus 5 by 2 of times z, and we substituted z equal to 1 for t less than tc, which gave us zeta 5 by 2, and since therefore I have a 1 by lambda t in the this goes as t to the power 3 half, since this quantity goes as alpha t to the power minus 3 half. So therefore I plot now this value is going to be 15 by 4 zeta of 5 by 2 divided by zeta of 3 by 2, right? And that is roughly 1.92, and yet we have another value which is 3 by 2, and that is the Dulong-Petit law. And then well, it looks a little ugly, so I think one has to be careful now. Let's draw it a little bit to scale. So this is roughly 2, and therefore this distance is 2, means this distance is 1, and therefore I have 1.5 as this. So this is going to be 3 by 2 approximately, and therefore one expects that the high temperature curve should look something like this. Right. So this is the classical limit, and this is where your critical temperature Tc is. It is continuous across the transition. The specific heat is continuous across the transition. Not only that, exactly at the critical point, its value is larger than the classical limit of 3/2. That is essentially of 3/2. That is the Dulong-Petit's law. The specific heat of an ideal Bose gas for T less than Tc, the specific heat goes as T over Tc raised to the power 3/2. Now, this result is for 3 dimensions, which means that the dimensionality of space is 3, d is equal to 3. Now we want to argue for any arbitrary dimension, and in fact we want to provide a physical intuition into this kind of a behavior for a Bose gas. Strictly at t is equal to 0, all the particles are in the ground state with epsilon equal to 0, and as you see, therefore the specific heat vanishes at t is equal to 0. Now suppose we give the system a little temperature kBT, which is very small. Now once you give this temperature to the system, then essentially you are exciting some of the particles, and the sum of these particles can go to the higher excited states. So you have a limit, right? Your free particle energy states have the energies h square k square over twice m, and when you give energy of the order of kBT to these particles, you can at most fill up certain number of your k's values, and that k values is given by h square km square over twice m is equal to kBT. So these km values are now occupied. So we will say so particles now have momentum up to km. They don't go above it because they do not have that sufficient thermal energy to go beyond that, right? Now the energy, it's a very simple understanding. The energy is proportional to the volume and to the density of state, which goes as km d minus 1. Now each of these particles which are now excited will carry an energy kBT, so that the total energy of the system now goes to proportional to V Km raised to the power T times kBT, right? Which becomes V kBT raised to the power D by 2 plus 1. I'm not worried about the factors over here. There is a proportionality constant. I can lump everything together in the proportionality constant. Once I have, if you look at this structure of the energy, so for any arbitrary dimension, therefore, the energy must go as T to the power D by 2 plus 1. Therefore, the specific heat, which is a derivative of this energy with respect to temperature, will be proportional to volume held constant, will be proportional to kBT raised to the power D by 2. And in then 3 dimensions, we have Cv over nkb going as T to the power 3 by 2 when we put D is equal to 3. So this is the more general result, and unlike a Fermi gas where your specific heat was proportional to linear, so one can write down this as Tv over Tc, and here we had T over Tf. This was for an ideal Fermi gas in any dimension. So for any arbitrary dimension D, your specific heat for an ideal Fermi gas was always linear. In contrast, for the specific heat for a ideal Bose gas will scale as T over Tc raised to the power D by 2 in any arbitrary dimension. Not in any, but we will say in D dimensions. So there is a remarkable difference for a Bose specific heat for a Bose gas and specific heat for a Fermi gas.